Hello, section 10.4, found in your book on page 563. Today we're going to be talking about the probability of disjoint and overlapping events. So first we have a bit of vocabulary. Our objective for today, by the end of the lesson, you should be able to find the probabilities of compound events and use more than one probability rule to solve real-life problems. Okay, so first, the union. The union of two sets. Okay, a union is when you consider all possible outcomes of two sets. Okay. How I like to think of it is for a union is if I let A be, let's say, all of the girls basketball players. And if I let B be all of the volleyball players. A union of these two sets would be all of the girls who either play basketball or play volleyball. Be all of those girls. That would be a union. And I would write that as A and then a big U, B, and a very big U, just a big horseshoe, A union B. That means I'm putting the two sets together and getting all of the outcomes from both sets. Whereas an intersection is just the outcomes shared by both sets. Shared should be a D by both sets. So over here, the intersection, and again this is written A and a big upside down U, B. This is the intersection of A and B. This is only the girls who play in both. Okay? They have a good picture here with some shading. So again here, if this is all the girls that play, if this circle is all the girls that play basketball, and this circle is all the girls that play volleyball, the union is all of those girls together. The intersection is just those girls who are in both sets. Okay, and if they don't overlap at all, let's say there's no girls who play both, they either play basketball or they play volleyball, then the intersection has none in it. Okay, a compound event is basically just a union or intersection. A union or intersection is a compound event. We either put two sets together, make one big set, or you look at just the ones they both have in common. So the union or intersection of two events is what we call a compound event. Okay. We call two events overlapping is if they have one or more events in common. If they have one or more outcome in common. One or more outcome in common. Okay. So the girls basketball team and the girls volleyball team will be overlapping if there's at least one girl who plays on both teams. Okay. And two events are called disjoint or mutually exclusive when they have no events in common. Outcomes in common. Again, my example of volleyball and basketball teams. They would be mutually exclusive if there was no girls who played on both teams. They have no outcomes in common. Okay. So to find the probability of a compound event. If A and B are any two events, and the probability of A or B, that's an important word there, or, let me get highlighter to yellow. A or B, this is one or the other happening. This is not the same as our, vocabulary, where'd it go? The conditional probabilities and independent and dependent. Okay, this isn't the same as independent. This is one or the other, not one and the other. If A and B are two events, the probability of probably A or B. So the probability of A or B equals the probability of A happening plus the probability of B happening minus their overlapping, the probability of A and B. You have to subtract off those overlapping. Okay, but if A and B are disjoint events, so if you can start with knowing they're disjoint, then the probability of A or B just equals the probability of A plus the probability of B. I don't need to subtract off the stuff they have in common because they have none in common. Okay, so let's look at a couple different ways of finding that probability. So here for extra example 1, two 6-sided dice rolls, so I'm rolling 2 die. What is the probability that the sum of the numbers rolled is a multiple of 4 or is 5? I'm looking for, is the sum a multiple of 4 or is the sum 5? So let's label these as A or B. Let's say the sum's a multiple of 4. Let's label that as event A. The sum is a 5. Let's label that as event B. Okay, so first I'm going to do is I'm going to solve this one by listing the sample space. So what are my possibilities of rolling 2-sided dice? So I could roll a 1 and a 1, 1 and a 2, 1 and a 3, 1 and a 4, 1 and a 5, or 1 and a 6. Could roll a 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5, 2 and a 6. Okay, could roll a 3 and a 1, 2, 3, 3, 3, 4, 3, 5, 3, 6. Could roll a 4 and a 1, 4, 2, 4, 3, 4, 4, 4, 5, and a 4 and a 6. Could roll a 5 and a 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, or a 6 and a 1, 6, 4, 6, 5, or a 6 and a 6. Okay, and so now I'm going to do a bit of color coding. Okay, so I'm going to circle in turquoise the ones that fit event A. So I want to get a sum. The sum is a multiple of 4. So we're looking for sums that are multiple of 4, so we need to add. That's 2, 3, oop, there's 4, 5, 6, 7, 3, 4, 5, 6, 7, 8, that's a multiple of 4, 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, 7, 8, 9, 10, 11, 12. Oh, looks like we kind of have the diagonals here. So here in turquoise are the ones that fit event A. Okay, now let's circle in purple here the ones that fit event B, which is a sum of 5. So now I need to figure out which ones have a sum of 5. So here we have 2, 3, 4, there's 5, 6, 7, 3, 4, 5, 6, 7, 8, 3, that's 4, there's 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, oh, nope, nothing's going to have a sum of 5, because we just want just a strict sum of 5, not a multiple of 5, sum of 5. Okay, and so now if you notice, the ones I have circled in turquoise and the ones I have circled in purple, they don't overlap at all. There's none that are circled with both. So that tells me that this is a disjoint event, because the outcomes don't have anything in common. Event A and event B have no outcomes in common. So to find the probability of A or B, I take the probability of A and add it to the probability of B, because these are disjoint. So now the probability of A. Well, for A, a multiple of 4. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 possible outcomes for a multiple of 4 out of 36 possible outcomes total. Plus the probability of B, 1, 2, 3, 4, 4 out of 36. So when you add these, we get 13 out of 36, which simplifies to, type in our calculator, 0.361. So there is the probability of getting a multiple of 4 or a 5. Okay, so rolling one or the other. So this example 1 is an example of a disjoint probability. That's example 1, disjoint. Okay, example 2. A bag contains cards numbered 1 through 20. One card is randomly selected. Okay, so that's fairly easy. We're just cards 1 through 20, so the sample space is the numbers 1 through 20. When card is randomly selected, what's the probability that the number on the card is a multiple of 3? Okay, let's have that be event A, multiple of 3, or a multiple of 4. event B. Okay, so let's list all of the possible ways we can get event A. That's a multiple of 4. Of 3. Okay, so again, I have the cards 1 through 20, so I could get a 3, a 6, a 9, a 12, a 15, or an 18. Those are all the ways I can get a multiple of 3. Hey, let's find a multiple of 4. So for B, we want a multiple of 4. Well, I could have a 4, an 8, a 12, a 16, or an 18. No, 16 or 20. 4, 8, 12, 16, 20. Yep. So those are all the ways I can multiply 4. But if you notice, they overlap because there's a 12 in both sets. So this is an overlapping compound probability. It is not disjoint. So to find the probability of A or B happening, I need to take the probability of A plus the probability of B and subtract the probability of A and B happening. Okay. So the probability of A, multiple of 3, well, there's 1, 2, 3, 4, 5, 6 out of the possible 20 cards. Okay. Plus the probability of B happening, there's 1, 2, 3, 4, 5 out of the possible 20. If you notice, I count the 12 in both lists because the 12 is in both lists. Here's where I take care of the 12. I subtract the probability of A and B happening. So I'm going to subtract how many are in our intersection, how many are in both sets. Well, only 1. So 1 out of the 20 would be A and B. So if I wanted something that was a multiple of 3 and a multiple of 4, there'd only be 1, number 12. Okay, so work this out. So 6 out of 20 plus 5 out of 20, that's 11 minus 1. So that'd be 10 out of 20, which would give me 0.5. So the probability of me drawing a card that is a multiple of 3 or a multiple of 4 is 0.5, 50% chance. Okay, this is an example of an overlapping event, an overlapping compound event. Okay. All right, let's do the next one. Okay. Okay, out of 45 customers at a breakfast cafe, so this is example 3, 42 customers bought either coffee or orange juice. There were 30 customers who bought orange juice and 40 customers who bought coffee. So you can tell just by those numbers, there were some customers that bought both. Because if we add these at 70, only 45 customers. So we have some that bought both. So let's kind of do a bit of a Venn diagram for this. We have 45 total in here. If we consider these are the coffee buyers and these are the orange juice buyers, let's let coffee be event A and let's let orange juice be event B. 42 customers bought either coffee or orange juice. So we have 42 customers in these two together. 30 customers bought orange juice, so these two together, so I've got basically 30 in this whole set. And we've got 40 in this whole set, but again, they overlap some. We've got this overlap. Hey, what is the probability that a randomly selected customer bought both coffee and orange juice? So really, we're trying to find the probability of A and B happening, meaning what's a probability that someone randomly selected is going to be in this group right there. So let's write, and this is disjoint, because we have, not disjoint, overlapping, because we have an intersection here. So let's write down our normal way. The probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Okay. So what's the probability that someone will have either bought coffee or orange juice? Okay, coffee or orange juice. Well, 42 out of the 45 customers bought coffee or orange juice. So 42 out of the 45 bought one or the other equals, what's the probability that someone bought A, someone bought coffee? The probability that someone got coffee, well, there were 40 customers who bought coffee, so that would be 40 out of the 45. Plus the probability that someone bought orange juice, that's B. Well, that would be my 30 out of the 45 customers. But we don't know how many bought both. That's what we're trying to find. We're trying to find the probability of A and B. So this is my missing piece right here. Let me grab another color. So really, we know everything but this. So we can actually solve for that. So I'm going to actually add this to the other side. So over here, I'd have 42 over 45 plus the probability of A and B equals 40 over 45 plus 30 over 45. Well, now let's take this thing here and subtract it to the other side, so we'll be just left with the probability of A and B. So the probability of A and B equals 40 out of 45, plus 30 out of 45, that's a 5, minus the 42 out of 45. So when we work that all out, we'd get, let's see, 40 out of 45 on our calculator, 40 out of 45, plus 30 out of 45, minus 42 out of 45, gives me approximately 0.62. So the probability that a randomly selected customer, out of the 45 customers that had breakfast at this cafe, the probability that the randomly selected customer bought both coffee and orange juice is 0.62%. 62%. Okay. All right. So example 4, this is example 4 in your book, but we'll work through it. Okay, we're going to have to use more than one probability on this one. Okay. The American Diabetes Association estimates that 0.83% of people in the United States have diabetes. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease and 95% accurate for people who do not have it. The medical lab gives the test to a randomly selected person. What is the probability that the diagnosis is correct? Okay. So really, you have two events here. We have event A, and that's a person has diabetes. And we have event B, they were correctly diagnosed. Okay. So event A is they have diabetes, event B is they're correctly diagnosed. Let's look at this one a little differently. I'm going to create a bit of a table. Hey, kind of a tree-ish diagram. So let's start. If this is the entire population of the U.S., population of the United States. Okay, we can divide them into two groups. Those who fit event A, those who have diabetes, and the probability of someone having diabetes is, if we get that to a decimal point, 0.083. Or not A, meaning they don't have diabetes. And what's the probability of that happening? They don't have diabetes. That would be, we take 1 minus 0.083, which is 0.917. Okay. Now, if you have diabetes and you take the test, so let's look here. A person who has, suppose the medical simple diagnostic test for diabetes, that is 98% accurate for people who have the disease. So if you have diabetes, your probability of event B here being correctly diagnosed, being correctly diagnosed is 95%. But your probability for not B being not correctly diagnosed then would be 0.05. Okay. Well, if you don't have diabetes, they say here, oh wait, we did the wrong, 98% accurate for people who have the disease. So this would be 98%. So this would be 0.02. Oh, wrong numbers. Read the problem one more time. Suppose that a medical lab has developed a simple diagnostic test for diabetes that is 98% accurate for people who have the disease. Yep. 98% chance of being correctly diagnosed if you have the disease, 0.02% chance of not being diagnosed. Okay, if you don't have diabetes, your event of B, of being again correctly diagnosed, would be 95%. Again, that would be correctly diagnosed, meaning the test comes out that yes, you don't have diabetes. Okay, or not B incorrectly diagnosed would be 0.05. Okay. All right, so this kind of just helps us see how this is working here. But what is the probability that the diagnosis is correct? Okay, so we want the probability that my diagnosis is correct. Well, you have we're doing basically two different probabilities here. You could have the probability of A, meaning you have diabetes, and they correctly diagnosed you. B, you were correctly diagnosed. Or the probability that you don't have diabetes, the complement of A, and you were correctly diagnosed. If you notice, this is both dependent events and a compound event with or in between. Okay. But we can see that these two are disjoint. There is nothing in common between either you have diabetes or you don't. There's nothing in both sets A and B. So this is disjoint. Okay. But I need to find the probability of A and B happening. So this is the probability of A given that B is happening. So the probability of A and B. So if you remember when we did our dependent events, this would be the probability of A times the probability of B given A. Or the probability of not A times the probability of B given not A. And since these are disjoint events, this one and this one are disjoint events, I can just take the probability of one and add it to the probability of the other. So then my or here in the middle is going to become a plus sign. So now I need the probability of A. Well, what's your probability of A? Again, A is having diabetes. 0.083. Let's multiply that times the probability of being correctly diagnosed given A. Well, if you're given A, if you have diabetes, your probability of being correctly diagnosed is 0.98. So we're going to multiply that by 0.98. Okay. Plus, since they're disjoint events, the probability of not A. Well, what's your probability of not having diabetes? Well, 0.917 times the probability of being correctly diagnosed given you don't have diabetes is 0.95. So times 0.95. So now let's go ahead and let's look at the probability of being correctly diagnosed. So I would take 0.083 times 0.98 and add that to 0.917 times 0.95. 0.952. So approximately 0.952. So the probability of just grabbing a random person off the street, running this test, and them being correctly diagnosed is approximately 95.2%. Okay. So here we had to use a couple different of our probability rules. Okay. We had to use the probability of dependent events for this part here, plus how to find the probability of a disjoint compound event. Okay. All right, so come to class with questions. We'll answer any questions you have and get started on the practice.